Hello, my name is Ryan, and today I'm going to show you the definition of a derivative. Alright, so the derivative is basically the instantaneous rate of change. So that basically means before, when we calculated the rate of change, we might have used slope, which is simply just the change in y over change in x, or you could say y1 minus y2, or x1 minus x2. And this is good, but this is going to actually show us, let me demonstrate. So this is going to show us more the average rate of change over 2 points. So if I pick this point and this point, this is going to be that slope, that average rate of change. So it's going to take 2 points and it's going to take the average. So let's say we wanted the derivative, which is the instantaneous rate of change. We wanted to say what's the rate of change at this point. Well, what we'd have to do is we could make a tangent line, so 1 point. So how we do that? So let's just call this point x. And then, so the output of this is going to be f of x, right? Just a function. So this is x comma f of x. And then up here, we have, let's call the distance between these 2 points h. So we can call this x plus h. So that means this, we put in an x, we get an f of x. Put in x plus h, functions take the f of x plus h. So then this is x plus h, f of x plus h. Alright, so now let's take the slope of those 2 points. So we know it's change in y over change in x. Change in y, so we're going to take f of x plus h, subtract that f of x, right? That's the difference between here and here, right? And then over here, the change would be x plus h minus x. And we can, x minus x is 0, so we can just move that, and we'll center that h. So this is the slope between 2 points in the graph. Now let's say if we wanted to make these 2 points 1 point, we wanted to bring them as closer together as possible, because this is pretty accurate. But as we get farther and farther away, this point to this point, that would not be a very accurate representation. So the closer and the closer together we get, the more accurate it is. So let's say we wanted to get as accurate as possible, which is just 1 point. We could take the limit, right? As h, this distance approaches 0, because we can't control this value. This is the dependent variable. So we're going to have to take as close together as these go. So limit as h approaches 0, right? So that means this distance approaches 0. If h is 0, then we don't have a rate of change. That's why we need the limit. If you don't know what a limit is, you can check out one of my other videos. Yeah, so this is what we call the derivative. This just gives the rate of change based on 1 point, or sometimes we call it the tangent line of a point. So that means, tangent just means it intersects only at 1 point. Alright, now I'm going to show you an example of how we can use this to find the derivative of another function. Okay, so now I have a function, and I'm going to show you how to do the derivative. So let's first, we know our derivative statement, which is the limit as h approaches 0 of f of x plus h minus f of x over h. So when we see this statement, f of x plus h, the normal statement is f of x. So we see an x here and x plus h here, which means we need to plug the x plus h in where we see the x. So we got an x squared, so that turns into an x plus h squared, plus 3x, which means just 3 times x plus h, and then a 2. And this is all subtracting f of x. We can literally just directly substitute f of x. This is f of x, so we're going to subtract this value. Remember, we have to distribute, because we're subtracting the whole thing, not just the first term. And then again, this is all over h. And then this is a limit as h approaches 0. Alright, so I'm just going to simplify. X squared, or x plus h squared is x squared plus 2hx plus h squared. And then this is just 3x plus 3h. And then this is going to be negative x squared minus 3x minus 2. I just distributed this negative. So let's just write this out. I'll speed it up for you. Okay, so now I have it all written out, and you can see a lot of stuff actually cancels out. So this x squared here is going to cancel out with this one. This 3x cancels with this 3x. This 2 cancels with this 2, leaving us with the limit as x approaches 0, or h approaches 0, sorry, of 2hx plus h squared plus 3h over h. So we can reduce an h. So let's reduce this, this, and this, and this. Since every term has an h, we can reduce, leaving us with the limit as h approaches 0 of 2x plus h plus 3 over 1. And now since the limit is h approaches 0, now it's not dividing by 0. Plug in 0 for h, so we put 0, so the derivative is actually just 2x plus 3. And I'm going to erase this, and I will show you again. So what we call the derivative f prime of x. That equals 2x plus 3. So now that basically means if I had this graph, x squared plus 3x plus 2, I'm not exactly sure what it looks like, but I think it's something like this. Yeah, that's not a very good drawing, but that's okay. No matter, depending on where the point we put it, let's say we put it at point equals 0. The velocity here, the rate of change, is going to be f prime of 0, or 2 times 0 plus 3, or just 3. 3 over 1 is the slope, or the m, or the velocity. If you've ever taken physics, this would be the velocity graph, and this would be the position and velocity graph. Yeah, so, and then over here, if we took 1, and x equals 1, we could go up here, and this would be a little bit steeper. F prime of 1 is equal to 2 times 1 plus 3, or 5 over 1. So that means there'd be a bigger slope. That means a variable slope, which is why we have an x in here. Alright, now you might be wondering, is there any practice problems for this? And I'm actually going to do something different, because that method that I showed you is it's called the definition of derivative. It's going to be it's a little bit more long-winded, so I'm actually going to teach you a quicker method, kind of a shortcut, that this is what you're going to use in every math class from here on. You're never going to have to do that definition of derivative unless your teacher wants you to on a test. And that shortcut is what we call the power rule. And there are tons of shortcuts for finding derivatives. This is the most basic one that can help you with just polynomials here. So this basically says if I had x to the n power, let's say ax to the n power, so this is the coefficient, this is the x, and then this is the power. So let's say it's like 3x to the 4th power. It equals the derivative of this. You can also write that as d over dx. That means derivative, same thing as f prime. That would equal a times n times x times n minus 1. So for this, that basically means bring the power down, the n, 3 times 4. Oh goodness, it's bad 4. Times x, and then subtract 1. So 12x to the 3rd power. So that is the derivative of this. So now if we apply that to this statement here, we see the x squared, we bring that 2 down, get 2x, then we subtract 1 from the exponent. 2 goes down to 1, we don't write the 1. We can bring this 1 down to the front here. 3 times 1 is 3. And then that x goes down to 1x to the 0, which is just 1. So we left with 2x plus 3. And the constant of derivative of a constant is 0. So we could just have the 0 here, but that doesn't mean anything. Derivative of a constant is always 0. Because if I had a graph of a constant, let's say y equals 2, there is no change in here. It's always 2. There's no rate of change. So, yeah. I can give you some practice problems for this, and I will show you a couple, actually. Alright, so the first practice problem is going to be f of x equals 6x to the 4th power plus 3x. Alright, so now find the derivative of that. I'll give you a moment to pause the video. Okay, so remembering our power rule, we can bring down the 4, get f prime of x. Bring down the 4, multiply by the 6, so it equals 24. Then subtract 1 from the exponent, x to the 3rd. Same thing over here. We can bring down the 1, it doesn't change anything. And we subtract 1 from the exponent, giving us an x to the 0. So just 24, x to the 3rd power plus 3. That is the answer. Alright, next we have f of x equals the square root of x. Now this one may look tricky at first, you may not know how to approach it, but we just must remember our exponent properties and exponents and radicals. So this is actually equal to x to the 1/2. And this, we can apply the exact same rule. We're going to bring the 1/2 down as a coefficient, and then we're going to subtract 1 from the exponent, so we have negative 1/2. And we're always going to want to bring the exponent down if it's a negative. We don't want to have a negative exponent. And a negative exponent, we basically just bring it down to the denominator. So 1 over 2x to the 1/2. All right? And that is f prime of x. All right. For our next example, we will do 1 over 2x to the 3rd. Alright, same principle. We are going to use the negative exponent rules. So we can take out that, we can change this to f of x equals 1/2 times 1 over x to the 3rd. Right? Because we can just separate that denominator into multiplication. And this 1 over x to the 3rd, we can actually just bring that up as a negative exponent. So I'll change that to x to the negative 3rd. So now we have 1/2 times x to the negative 3rd. We can bring out that we can bring this down front using the power rule. So f prime of x equals negative 3 over 2 times x. And then we're going to bring that down, this power down 1 to negative 4. So now we have negative 3 over, and we can bring this down to the denominator, 2x to the 4th. And that is f prime of x. Alright, I will do one more example. The last example is going to be 10x to the 2/3. Alright, I'll give you a moment to try this on your own. And now I'll do it. So, we're going to start by taking that 2/3, bring it down to the front. So 10 times 2 over 3. This can be all over 3 times x. And then 2/3 reduced by 1 is negative 1/3. So 10 times 2 can be simplified to 20. And then this x to the negative 1/3 can be brought down as an x to the 1/3. And that is the derivative of this function. If you enjoyed this video or found it helpful, please remember to like the video, and thank you for watching.